So we shall continue our previous discussion on total internal reflection, right? And so we can again a little bit of recap of what we discussed for our interface, and suppose interface is defined like this: N1 and N2, and then in the interface, if something comes, some electromagnetic wave making an incident here, I think, yeah, so a little bit. And then it will be reflecting, and something will go to the second media. So this will be called as a theta I, this is theta R, and this will be theta T. Okay, so we have distinguished two types of polarization, TE, and then another is TM type. So when we are calling TE, electric field is perpendicular to the screen, and when we are calling TM, that means magnetic field is the perpendicular to the screen. And this is what propagation direction we defined: KI, KR, KT. Okay, so we can put vector sign. So these are the case, and then we have this reflection coefficient. For I will be just talking only reflection coefficient. We will not concentrate much on transmission coefficient at this point of time, because they are obvious because of the equation. So we have the gamma T. That means if it is T polarization, electric field is in the perpendicular, oscillating perpendicular direction of this screen. You can just imagine, probably this is your x-axis and this may be your z-axis. Sorry, this should be your z-axis. For reference purpose, we just continue to do this. So if electric field is in perpendicular to the xz plane, then we call it gamma TE, right? And the expression we have already discussed earlier: N1 cos theta I minus N2 cos theta T divided by same thing but plus cos theta T, and gamma TM equal to, you have your N1 cos theta T minus N2 cos theta I. Similarly, denominator is same but plus sign. All right. So this is your Fresnel equation for TE and TM. Now we have discussed the first case, that N1, if it is greater than N2. So from Snell's law, if I just try to write down N1 cos theta I should be equal to N2. Is a cos or sine? Snell's law?
Sine.
Yes. So it is actually N1 sine theta I equal to N2 sine theta T. So obviously when N1 greater than N2, we can say that theta I should be less than theta T. Is that correct? Because to satisfy Snell's law, this is your Snell's law, right? That can be proven from your Maxwell's equation, boundary condition, Snell's law. So to satisfy Snell's law, if N1 greater than N2, N1 greater than N2, that means sine theta I should be less than sine theta 2 to satisfy Snell's equation. So once sine theta I less than sine theta t, that means I can say that theta I less than theta t. So that means whatever I have sketched, theta I should be less than theta t. That is not the case. Looks like that theta t is a yeah, theta t is bigger, right? So it is not going in this direction, right? It is bigger. So this type of situation can be valid. So I cannot find a condition theta I where theta t can be greater than or equal to 90 degree. So theta t should be always, is that correct what I'm writing? No, I am not correct. I just first want to discuss other thing because I have written something else, I'm talking something else. So let us consider something like this. N1 less than N2, then what will have theta I. First I want to discuss this, then I will come to that point. Yeah, that is what I have done. So is N1 less than N2, that means theta I greater than theta t. So that means theta t always is less than 90 degree. Is that clear? Hopefully it is clear, right? So theta t always will be 90 degree. Theta t will, because theta I can be maximum 90 degree. If theta I max, if I just say theta I max, if I say that is actually 90 degree, minimum is 0. So that means theta t must be less than 90 degree. That much is clear. So for this condition, any wave, electromagnetic wave, that can be either TE or TM or any other polarization mixture of these two is coming, then I think this is actually always true that something will be transmitted to the second medium, okay, and something will be reflected to the first medium. So that much is correct. So now case 2, where I am considering N1 greater than N2. So again, if I just follow the Snell's law, that means I have to say theta I should be less than theta t, right? Theta I should be less than theta t. Since theta I max is actually, again, theta I max can be 90 degree. So in between you can find a value theta I equal to theta c, that is the critical angle when theta t will be equal to 90 degree. So if in this type of situation, what is happening? Okay, that is not this case. Just hold on 1 minute, I have some problem here. Okay, fine. So theta I equal to theta c, then theta t equal to 90 degree. So in this particular situation, we can call it as a critical angle, and then at this critical angle, it is we can write that sine theta c should be equal to sine inverse of n2 by n1. Okay, that is the expression. So between two media, if n1 greater than n2, then obviously sine inverse n2 by n1, n2 by n1 less than 1. Obviously that is correct. Sine inverse n2 by n1 less than 1, and that is actually measure the critical angle, where we are sure that your transmission angle or refracted angle should be 90 degree. So if we just go back to Fresnel's equation and try to put down here, then what we will get that particularly when I putting sine theta c equal to n2 by n1 and theta t equal to 90 degree, in both the cases, if you see theta t 90 degree, theta t 90 degree, that means one of the terms in the numerator and denominator will vanish. And if that vanishing condition is fulfilled, then gamma, whether it is T or Tm, that should be equal to 1. That is actually the condition for total internal reflection. We can say that totally it is getting reflected. But what now today what we will discuss, that what is happening when your theta I, if it is greater than theta c. That means theta I, if it is greater than theta c, normally from our school knowledge, we also know that total internal reflection takes place for the same thing, N1 greater than N2. And this total internal reflection can take place for both polarization TE as well as TM. Okay, as long as you are considering that T and TM, their refractive index are same for in a medium. That means it is isotropic medium if you are considering, or isotropic medium. Isotropic, of course, we are talking about homogeneous medium. Homogeneous and isotropic. You know what is the difference between homogeneous and isotropic, I guess. I don't need to repeat that. All right, let us stick to this point here, because this is more important. When theta I greater than theta c, that time what is the situation comes for theta t? Theta t, according to the Snell's law. According to the Snell's law or Fresnel's law, we can try to little bit interpret what is going to happen to theta t, because exactly at theta equal to theta c, theta I equal to theta c, we have learned that theta t should be equal to 90 degree. It will be becoming, as theta I increasing from 0 to higher values to theta c, then theta t equal to 90 degree. Then we are thinking that what happens if theta I greater than theta c. Okay, so if theta I greater than theta c, let us come back again to this reflection coefficient. Let us concentrate only on one polarization, TE polarization. TM polarization, you can follow it up. I don't need to discuss here. Just one polarization I'm concentrating to understand the consequence. Okay, let us just repeat the expression once more for completeness. N1 cos theta I minus N2 cos theta t, and N1 cos theta I plus N2 cos theta t, right? So since theta t, what is going to happen for theta t, we don't know, but at least we accept that N1 sin theta I equal to N2 sin theta t, that is coming directly from the Maxwell's equation, boundary equation. So we can say that this is actually coming from Maxwell's equation. This has to be, whatever situation, whatever consequence happens, this has to be maintained. And we cannot also rule out Fresnel's equation also, because Fresnel equation also derived from boundary condition, which is actually universally true, and that cannot be ignored. Any paradox coming, that is our intelligence, we have to interpret what could happen and what is the consequence. Okay, because these are coming from fundamental theory, we have to actually accept it. Otherwise, we have to revolutionize the theory. We have to change the theory. That is, I think, we don't need to bother about in this course as of now. So now, since theta t is a point, we are not really knowing what is the value, what could be the result. So what we could do, at least we can express theta t in terms of N1 and N2 and sin theta I. Because incidence angle, this is in our control. This is a parameter we can handle. We can shine a light in the interface at any angle. So that is in our hand. What is happening to theta t, that is the consequence, that is the result that we will try to understand. Okay, so if this is the case, then we can easily write cosine theta t. Why I am writing cosine theta t? Because here cosine theta t is there in the numerator as well as denominator. So we'll write 1 minus sine square theta t, right? So that can be written as this thing, 1 minus N1 by N2 square sine square theta I, right? N1 minus by N2 whole square sine square theta I, that is the cos theta t. So we write that one here in this equation, gamma TE equal to N1 cosine theta I, that is our incident angle. I know that is in my control, and then I can write n2 square root of 1 minus n1 by n2 square sine square theta I, and n1 cosine theta I plus n2 square root of 1 minus n1 n2 square sine square theta I. Okay, so far so good. Now you think that if theta I greater than theta C, first of all, try to see when theta I equal to theta C, what is happening to this thing. Just put theta I equal to theta C here. What will happen? Sine theta C. Sine theta C value is what? We know what is the value of sine theta C. So sine theta C equal to n2 by n1, right? Sine theta C from here we can write easily sine theta C equal to n2 by n1. No, n1 by n2, right? Sine theta C equal to, yes, n2 by n1, correct. Sine theta C equal to n2 by n1. Because Fresnel's, according to the Fresnel's equation, sine theta t will be equal to 90 degree. So theta c, we are defining that. So when theta equal to theta c, that is n2 by n1, obviously it is coming like a 1 for theta equal to theta c. But our concern is what is happening to theta I greater than theta c. Can you just think of what would be this value? What would happen to this? This under square root, whatever this thing will be there, theta I greater than theta c. Anyone can answer to this?
So this one should be greater than 1. So 1 minus greater than 1
1
something
is something imaginary.
imaginary quantity will come.
Yes. So that means if I just slowly increase the theta I, if I just concentrate only on the second term, theta is starting from 0 and keep on increasing. That means this value, when theta equal to 0, it was 0. Now theta increasing means sine theta normally it will increase as a function of sine theta. You know, from 0 it will be increasing sine theta. And when it is exactly theta c, that is actually n2 by n1. That means this is cancelled. That means 1. So 1 minus 1, 0. So when theta is greater than theta c, obviously this value, this particular value, if I just mark it, this particular value will become less than 1. Greater than 1, sorry. That should be actually greater than 1. This marked region should be greater than 1. So once that is greater than 1, so we can define that that one as something. This one I can just I am defining like this, that okay, I think I can directly write without any further step. I can just directly write like this: a minus jb divided by a plus jb. Is that correct? Where we can define clearly, this is actually b equal to n2 n1 by n2 square sine square theta I minus 1. That is your b. That means b is a positive value, because this is actually greater than 1. So b is a positive value, positive number, or whatever value comes. So I can write a minus jb by a plus jb, right? So this is a good one. So we write here once again, we write gamma te equal to a minus jb divided by a plus jb. Okay, so where a equal to n1 cosine theta I and b equal to, so n2 n1 by n2 square sine square theta I minus 1. So this is the case we are considering when n1 greater than n2 and theta I, of course, greater than theta c we are considering. Then if this is the situation, B is a positive quantity. B is a positive quantity. Obviously, A is also a positive quantity, right? So this is the case. If I try to do, this is the complex conjugate. Numerator and denominator is a complex conjugate. We can write something like this, you see. A square in polar coordinate system, we can write something like this. J phi. We just define like this. Say phi t we can write. That is for t polarization, maybe we can write, and divided by a square plus b square times e to the power j phi te. What is the value of phi te? So phi te will be actually tan inverse b by a. Is that correct? So it is a complex form. Now I am just writing in phasor form. So that means this one, this magnitude is same, numerator, denominator. So we get what we get? We get 1 e to the power minus 2 phi te. Okay, or maybe we can just put a phi prime here. Better we will be just writing this one. Is that correct? That can be written as 1 minus, sorry, not minus. That can be written as 1 magnitude here and e to the power j phi te. Minus sign we can put. So here phi te equal to phi te prime plus phi te prime. So equal to 2 times tan inverse b by a. 2 times tan inverse. So phi te we have defined. And b value, this one, and a value is this one, right? This one we should keep in mind. So what we are getting, gamma t. Gamma t means that reflection coefficient. Reflection coefficient means I can say that what is the value of reflected light divided by EI. I think we should not write this thing. So if this magnitude is there, this one, I can write ER0, EI0. ER0 is the amplitude of the reflected wave and EI0 is the amplitude of the incident wave. That is actually this one. So what does it mean? ER1 equal to EI0 e to the power minus j phi te. So what you interpret from here? What is this? So that means we say that the reflected wave actually coming out, whatever vector is there, you can write. You can, this one is there, I0, whatever vector direction you can assign. That means incident wave is reflecting along with a phasor part like this. So that means it is a total reflection taking place. Whatever incident, everything coming as it is, but it is included with a phase. So that means when theta I greater than theta c, then it is also happening total internal reflection, but it is also happening total internal reflection. But what is happening with that? The reflected wave gaining some kind of phase. Is this clear to all? Rishabh?
Yes, sir.
Abhinav?
Yes, sir.
So good. So then what is this interpretation? Total internal reflection, and there will be some kind of phase acquire. when reflecting. So this is very, very important, that when total internal reflection takes place, then it is just not enough to say that everything is reflecting back, power is reflecting back, but we have to consider that phase. Why that phase is important? Anyone can tell?
Yes, sir.
Why?
Actually, because of path length, there will be phase, and because of reflection, there will be phase. So when these two phase will add equal to 2 pi, so constructive interference will happen. So this is
Because
very important.
normally whenever we are talking about integrated optics, electromagnetic waves, we have to consider the field amplitude, not that power or intensity. Okay, what is the strength? And when we are talking about more than one electromagnetic wave in a certain point, what is happening to that one, we have to consider their phase information as well, because all these superposition principle works for electromagnetic wave as well, but the superposition principle is not valid for intensity, but rather it is valid for field strength. So field strength, if it is actually associated with phase, suppose it is one field is coming like that, and another field is coming with another amplitude, and you have to consider the phase. Then only you can see that what is the total effect. But if you just consider intensity plus intensity of one electromagnetic wave, what is the intensity? That means total power per unit area, and another electromagnetic wave with another intensity. If you add, that will not actually work correctly, because sometimes phase information can cause some kind of interference, that can be destructive interference, that can be constructive interference. That's why phase is very important. So you have to consider this phase, what is happening during the total internal reflection. Okay, so in a same fashion, if I just give you a home task, you will be able to find that if it is a TM polarization, this phi TM will be actually equal to 2 times tan inverse, okay, N1 by N2 square sine square theta I minus 1 divided by N2 cos theta I. Okay, so I have just written B and A. Phi t also similarly we should write phi t equal to 2 times tan inverse B by A, right? What is that? N2. So for in this case, N2 square root of N1 by N2 square sine square theta I minus 1 N1 cos theta I. So this is your phi t. Okay, so that means if you are just considering simply a expression, that is not enough. You need to visualize this. So this phi TE and phi TM, that means phase, when it is total internal reflection, this is two happening when it is total internal reflection. If there is no total internal reflection, upon reflection, you will not get any phase change. It will be coming like that, n greater than n2. Now, my question, do you see that phase change is happening as a function of wavelength? If you change your wavelength, this phase change will be different or not?
Sir, because of our diffractive index, until our diffractive index is constant with wavelength, then it's okay. But refractive index sometimes function of wavelength, then it will affect.
Correct. So as long as the refractive index is constant for wavelength, then it is actually the phi t and phi tm is same. And obviously it is not correct. But any material medium, any two medium, if you are considering, the refractive index is not same unless and until it is a free space. Free space refractive index is 1. Okay. Otherwise, most of the material we find, refractive index is a function of wavelength. Typically for normal dispersion case, as you increase the wavelength, typically if you see, if lambda and refractive index, if you see, for normal dispersion, it will be looking like this. The curve will be looking like that. Longer the wavelength, refractive index will be dropping. Okay, it's a normal dispersion. That sometimes it will be some abnormal dispersion will be there. That is actually during resonance or absorption. So that thing I'm not talking right now. Okay, so this is the normal case. As a function of lambda, then refractive index will be dropped. But as long as we are sticking with a single frequency, single lambda, then normally TETM will be like this. And also TETM, we are considering that refractive index for medium 1 and medium 2, they can be also different for T and TM if the medium is anisotropic. Okay, so that those things you should keep in mind. So let us stick to that N1 greater than N2 and refractive index, whatever a single wavelength is fixed. Other than that, this phase actually depends on theta I, right? Now, if I ask you quickly, looking into the expression, just look into the expression. If I just vary theta I, so for total internal reflection, theta I has to be equal to theta C or greater than theta C, right? And it should be less than 90 degree or pi by 2, right? Now my question is, as you increase theta I, what would happen to the phase? Because total internal reflection, it's a band of you have to consider a band of angle. So greater than this band you have to consider. So obviously you see from this equation that phase is actually depends on theta I. As long as you are considering lambda is fixed, as long as you are considering N1 and N2 are fixed. So my question is, as you keep on increasing, suppose if I ask you to plot, right, say theta I starting from 0 to pi by 2, and if I ask you to plot phi TE or phi TM, let us consider phi T, how it will be looking like. Suppose N1 and N2 is given. N1, suppose it is given for say 3.46 and N2 is given actually 1.46. This is corresponding to silicon material and this is corresponding to silicon dioxide approximately at lambda equal to 1550 nanometer. So just a typical value I have given. And if I ask you to plot this one, how it will be looking like? Can anyone help me?
Sir, there will be a maxima at sin theta equal to N1 by N2.
What would be the value at theta equal to 0?
So there won't be a phase until theta C.
Exactly. That is what I mentioned. Suppose up to theta C, we don't need to bother about that because it is this equation also will give that.
Then
So
afterwards,
this phase only valid, this expression valid only when we are considering theta greater than theta C, greater than equal to theta C. So this range valid, yeah, we have to see. And before that, we have already found from the Fresnel reflection equation that if theta I less than theta C, no phase change will be there. Only a certain case when N1 greater than N2 or N1 less than N2, that time pi phase shift will be there. That also you can conclude from the Fresnel's equation. Now, so up to theta C it is okay. Now from theta C to pi by 2, what would be the value? Exactly at theta C, what would be the value?
0.
0. Fine. So one value is fine. This is one value I am getting here. What would be the value at pi by 2?
Pi by 2.
So pi by 2 will be pi by 2. If I just theta equal to pi by 2, that value is 1, right? Sin theta equal to 1, right?
Yes.
Then
And cos theta is equal to 0.
cos theta equal to 0. So then it is infinity. So 2 tan inverse infinity means how much? Pi by 2.
Sir,
So
pi, sir.
tan inverse pi equal to infinity.
2
Is that
tan
correct?
inverse. 2 tan inverse infinity, so 2 into pi by 2.
So that will be pi.
Yes.
Okay. So that will be pi. Correct. So in that case, if I just write pi, so one point you will be getting here. So that is corresponding to pi. This one will be another point. So you can imagine that something will go like this, right? So that is for phi t. What about phi tm? Will be same.
Similar, sir, but it would be a bit higher than this graph.
Because you have n1 by n2 is there, and here n2 by n1. This is n2 by n1 and this is n1 by n2, right? Other than that, inside is almost same, right? So this n1 by n2 or n2 by n1, normally I know n2 by n1 is lower and n1 by n2 is higher. So in that case, you can imagine Tm will be something like this. But exactly at pi by 2, it will match, right? So they will be actually different, T and Tm. Curve will be different. I suggest you to plot this one and check. Use this example, these parameters. You can just use MATLAB program. All of you know MATLAB program. Now, if you don't know, you just sketch. So assignment. This one is the assignment to plot phi t and phi tm, because that will be giving you a better feeling. Assignment, and you submit to our, I think our TA will put up as an assignment problem, and you can submit in the Moodle. Is that okay?
Okay, sir.
Good. Now we move on to one interesting point. Let us go back to our this thing. So I have time here. So I have media, and this is your interface. I consider N1 and N2 non-magnetic dielectric material medium, and we also consider N1 greater than N2 where total internal reflection takes place, and we also consider this is actually z-axis, and we consider something, this is your x-axis. Okay, and let us consider wave is coming and making an incident at an angle theta I, and this theta I, suppose you are considering, is greater than theta c, right? And then you know what is happening. I know that everything will be reflected back. So that will be your theta r, and when it is reflection, always that should follow also reflection coefficient, reflection law. That means theta I equal to theta r should be greater than equal to theta c. So total internal reflection taking place. So this is total internal reflection, it is taking place. I write here TIR. And I know that when total internal reflection taking place, that time you have to have some kind of phase. That for TE it is some phi TE, otherwise phi TM phase will be there. So normally what happens, actually first time it was found, and also we know that for exactly a total internal reflection, the transmission we found, you can remember earlier someone argued that transmission will be 2 times exactly at theta equal to theta c, tau equal to 2 times of, because gamma equal to 1, tau equal to 1 plus gamma, something like that, tau 2. So that means you have a field strength in the second medium according to the Fresnel's equation, and at the same time according to the Fresnel equation, I see that totally, when it is totally reflected, it acquires some kind of phase. So our concerns, just to interpret that, what is that actually? That is actually nothing but we assume that the field actually penetrates a bit and return back. And that penetration, as you I think Abhinav was saying that total internal reflection phase change will be there, that has to be included, and other phase is coming because of the path length difference. So we can consider this phi T and phi Tm as if it is some kind of delay happening while occurring total internal reflection. So that means this these things just somehow penetrate a bit and comes back, but it does not go everything. The power cannot flow to the second media. It go inside a bit and comes back. So that has to be actually quantified, how much it can go inside. So that also we can relate that, you know, that electromagnetic wave, when it falls into a metal, skin depth is there. Up to a certain length it will be attenuating, because inside metal electric field cannot exist, right? So because of the metal, sigma is very high, conductivity is very high, so field strength will not be there, only normal component will be there in the surface, so tangential component will not be there. That's why actually it penetrates and it decays up to the skin depth, and mostly in the within that skin depth, if it is not really absorbing, then it will be reflecting back. So here also you can actually, from the Frenon's law, when it is total internal reflection, that is actually for normal conductor you are considering at any angle, that is true. In a metal, at any angle electromagnetic wave comes, metal with high conductivity, so normally it will reflect up to the penetration depth, skin depth, it will be decreasing. But here, when it is total internal reflection takes place, when two media dielectric, lossless, sigma equal to 0, we consider, right? Lossless. So then also total internal reflection taking place, but we can actually analogously think something that there can be some kind of skin depth. So electromagnetic wave penetrates a bit, and slowly it should actually attenuate. So attenuation is field strength will be attenuating as you go deeper and deeper into the second media, and that attenuation will be reflected in the whatever energy is being reflecting back to the second media. So that actually called some kind of delay happening here. That means some when it is there, some you can say that when it is hitting here, it little bit shift and then comes back. Sometimes in older days, it is actually used to call it as a, like a Guj-Hansen effect. So that is actually two scientists, depending on the first time they discover and detected experimentally that it is, even though it is total internal reflection, some field is actually present in the second media. So that is actually Guj-Hansen shift. That means you are imagining that, okay, upon reflection, it actually emerge from the second media at some different point, because it goes a little bit inside. We can imagine some point it is going inside and then coming back. And so.
Sir, I have a question. Sir,
Yeah.
that means if I deposit the layer of N2 very small, less than my penetration depth, then there will be N1 medium. Then I have a very definite probability to get the field again.
Yes, yes, very much. That's very important.
Means analogy to quantum tunneling, like
Exactly,
that.
exactly. Quantum
Okay,
tunneling, how we interpret there, because we consider quantum particle like electron, they are like a wave, and it follows the wave mechanics like Schrodinger wave equation, and wave also they satisfy certain kind of boundary condition, and it is also happening tunneling there. Since, and that tunneling only you can interpret because you are assuming quantum particle like a wave. It is also a wave. And if, as you said that, if you are just considering a small layer, you are considering of N2 and then again N1. So there also there will be some kind of, that is called actually frustrated total internal reflection. It will be frustrated because within the penetration depth, your N1 is again coming back. So it about to take total internal reflection, but not happening because some penetration is there, and once it is penetrating again N1, and that will be like a wave again. So that is actually tunneling. That's exactly correctly you mentioned. Okay. Now my understanding is that to design a device, integrated optical device, you know, you have to have your waveguide, you have to have different type of material, you have to integrate. Heterogeneous material will be there, monolithic integration, even you can etch, all those type of things is there. So always you have to deal with interface. And in the interface, you have to deal with whether it is a total internal reflection taking place, or or it is just penetrating, tunneling completely, or some reflection is taking place. So if it is total internal reflection taking place, then how much it is going that side, so that I don't need to put any other foreign material close by, so that total internal reflection will be frustrated. I want total internal reflection, But that total internal reflection should not be frustrated due to the presence of the second foreign material nearby. So that is one of the important parameter for designing our devices, integrated photonic devices, particularly waveguide based devices. Now, suppose I know lambda is known to me, and I know theta I is also known to me. Some value is given greater than theta c, known. So that is known, and that is known. Can we find how much it will be penetrated? What is the depth of it? Because that is very important to know to design our integrated optical devices. I need to know how much it penetrates so that I can not think about bringing another one device close by within that range. Just that type of penetration depth is needed. So how to process it? Anyone can help? How to process it? If you are not asking, I will ask someone. Tell me. Ankita, tell me. How to process it? So you understand that there will be some kind of penetration will be there, but I have to quantify how much it can penetrate. N1, N2 known. N1, N2, these two also known. So how to find? It will be penetrated, but how much I want to find?
Sir, we have to write a field equation in board medium. Then we have to substitute one by one to get the field on the second medium. Then we'll have a field formula, and yeah, from that way we can.
So I'll go a little bit very easier way to find out. What you said, that is one thing. You just use your all field equations, you use Maxwell's equation, and then you solve Maxwell's equation at the interface, and use this boundary condition, and then try to see what is the solutions you are getting. That's one way. Let us try a little bit simpler way. What I said, what I assumed that actually you have your some penetration is there, and you know when theta equal to theta c, that means what is happening to theta t beyond 90 degree. Theta equal to theta c, theta t equal to 90 degree we know. For theta I equal to theta c. But theta t will be 90 degree. But what happens to theta I when it is theta t when theta I greater than theta c? Let us assume that someone was saying in other class that you have to consider theta t imaginary. Some imaginary value will be there. That is for sure, because theta t, if it is greater than 90 degree, it is not really, you are thinking the wave is in the second media. But you see that there is a possibility that because phase is there from the Maxwell-Fresnel's equation, we are forced to think that something electromagnetic wave is there in the second media. So I can just imagine, okay, forcefully I imagine that, okay, some Fixius. Okay, let me just do like this. Some say Fixius field is there, and their propagation vector is this kt. Just imaginary, we are just considering. Some theta t you have to consider imaginary, right? I just consider that one is theta t. And assuming that existence of that, some wave is propagating in that direction. I want to know what is happening to this kt. Meaning, I can find out what is this kt z component and what is happening to this kt x component. And you know, if this wave vector, when I decompose that thing, that means I can say that transmitted wave that will have two components. If it is they are real, that means kt is real. Is that clear? If I can prove that ktz is real existing, then kt will be real. And kt, one of them if it is imaginary. That means this is a complex thing. Some complicated situation will arise. We'll show that if this condition fulfilled, N1 greater than N2 fulfilled, then this KTX also you will get a solution, but imaginary solution. So when it is imaginary solution, that means in an electromagnetic wave, if your K vector is again imaginary, you know that e to the power electromagnetic field is e to the power j omega t kz, some z direction if it is propagating. If this K becomes imaginary like j kappa, what will happen? This j will be there minus j, for example, you are considering. Then what happens?
Attenuation, sir.
It will be attenuation. So that means KTX, if you can show that for theta I greater than theta c, KTX becoming imaginary, negative imaginary value like this, then what happens? That wave cannot propagate there in that direction. So it will be attenuating. That means energy cannot be carried away to the second medium. But if KTX is imaginary, but KTZ can be real. That means when KTX is imaginary, KTZ is real, that means we can still consider something is existing along Z direction. Okay, so if you can just try to find out what would be the expression for KTX, then probably you could be able to answer what would be the penetration depth. That means it will be imaginary, means it will be exponentially decaying along X direction. And if you just find 1 by E depth along X direction, that will be the penetration depth. And you can just find, okay, you can just leave 5 times of penetration depth, then you can bring another material or another device close by, then it will not be affected. So that type of exponential nature always in the electrical circuit also we use. You know, if it is transient case happening, exponential decaying, so we have to actually allow some switching time to switch on again for any circuitry, right? So switching on off time, that is actually RC constant is very important. Here also you need what is the decaying length, then only you can bring your second device. That if you are bringing your second device close by to that within skin depth or that penetration depth, then you are interfering your device property. So some power will be leaked. So I suggest you that you take, I just stop here today. You take this as another second assignment for a given N1, N2, same value I have given. N1 equal to 3.46 and N2 equal to 1.46, lambda equal to 1550 nanometer, and then theta I you consider, say some angle you consider, theta equal to probably you consider about say 75 degree. Theta equal to 75 degree, that is more than your critical angle, right? Then you find what is the skin depth, or I can say that you just plot that skin depth or penetration depth delta as a function of theta I for a given value. So you have actually calculated phase as a function of theta I. You also calculate delta, that means penetration depth, as a function of theta I. That can be your second assignment. Suvarna, you note down here. Okay, I stop here. If you have any questions, you can continue. Otherwise, I stop there.
Sir, it means some power is leaking in the second medium, no?
No, field strength. I am talking about field strength. Power will be there. The field strength is there, means intensity will be there, but power will not be carried away to the second medium. That is the major catch here. You have to understand this. The field will be existing, but energy will not be taken away by the second media.
Okay, sir.
That is how KTX we are arriving to as a imaginary. If KTX is imaginary, that means you cannot think of energy as being, because energy, you know, E cross H, Poynting theorem. So if E is slowly decaying, and up to sometimes it is non-zero, completely becoming near to zero. So no energy can go that direction, right?
Okay, sir. Thank you, sir.